Good afternoon, everyone. Thank you for joining us today for Piping Fundamentals. My name is Sunday Perez. If you haven't been on one of our classes, I'm the Corporate Marketing Manager, and our illustrious instructor is Paul Campbell, our Corporate Technical Trainer. If you have any questions, we have a couple ways to chime in. There's a little thing that looks like a deck of cards with a Q on it. That's our Q&A section. But if you are in the habit of using the chat function, don't worry, I'm covering both. I got you. Paul will break if we have some time to answer some questions throughout the training, but we will have some time at the end to cover anything that comes up. I know last session we had quite a few questions pop up right at the end. Totally good. We'll have enough time to do that. With that, I'm going to hand it over to Paul, and I hope you enjoy the class.
Awesome. Thank you, Sunday. And again, thank you to everyone joining us. I know if you're like the rest of us, you're inundated with Zoom meetings, so we appreciate you taking a few minutes out of your day here. I just wanted to cover some fundamentals as it relates to piping, piping schematics in general. Nothing we do in the hydronics industry or hydronics world is very complicated or rocket science. It's not like we're having to land, it's not like SpaceX where we're trying to land a spacecraft vertical at the end of its flight. That can get a little tricky. But listen, we just want to cover some fundamentals this afternoon and make sure that everybody's on the same page as far as the difference between primary, secondary, primary only, some of the challenges we see, and then we'll look at some actual examples, and we'll talk more about them as we go. All right. So let's with that, let me get started. A preemptor here. We see a lot of issues in the field. Specifically around boilers, but it could be around pumps and chillers, whatever you want to call out. A lot of it are venting issues, venting challenges. We'll spend more time on that when we get into boiler fundamentals. Guys doing retrofit, taking a condensing boiler into an existing galvanized flue. You can't really do that. You can try, but it's not successful. We see architects sticking us into basements, and we're having to deal with sidewall venting. That creates some challenges. Also, flue gas recirc that gets drawn in through our outside air challenges. We see engineers designing jobs where it gets very cold, like Fairbanks, where it might hit minus 40, minus 50. And they forget that if you sidewall vent boilers or water heaters, that now creates a new amenity for the hotel called an ice climbing wall. Okay, that's pretty rare, but it does occur. You got a few rooms that are hard to rent out. The view sucks, and the PTAC units aren't working so well. But they're all challenges. Maintenance is another one. We see a lot of guys who want to go high efficient condensing these days. It all makes sense, but you have to maintain that equipment on a regular basis. Otherwise, no worky. Efficiencies aren't very good. Okay, all these are kind of challenges to our industry. And ultimately, you know, the mindset is, hey, let's put something in a closet and come back in 10 years and check on it. And if we're having problems, maybe it's easier just to go to Home Depot and get the biggest C-clamp we can find, so we don't have to come in and reset our manual reset high limit every morning in an effort to keep the building warm. Well, this is one approach, but you also have to realize you got a bomb in your mechanical room, and that's probably not the smartest option there, okay? So we've talked about maintenance, we've talked about venting challenges, we've talked about, I don't want to say incompetence, but some issues in the field. Another one that we see on a regular basis is piping. And believe it or not, that does get screwed up. So we just want to cover some fundamentals here yet and make sure everybody's pretty solid. So let's talk about an old school design, because if we go back a few years, this is a probably really easy place to start. Old school, we used a lot of three-way valves out in our system, okay? If each one of these zones or buildings or campuses, however you want to look, office buildings, if each one of these is sized for 100 gallons a minute, then you could kind of make a statement that whether we're sending hot water to this valve or this zone, or we're bypassing, that we're always moving 100 gallons a minute in this circuit, okay? I know it's not linear, but just nod along and say, yeah, that makes sense, okay? So if we're sending 100 to this circuit, we're also sending a constant 100 to this next circuit and 100 to the last circuit. So our pump is always seeing a flow of 300 gallons a minute, and as is our boiler. Okay, now we could put a VFD drive on this pump, and assuming that we might pick up some energy savings, but the reality is we will never fluctuate below 300 gallons a minute because we always are bypassing the same flow that we could potentially send to a zone for heating. Okay, everybody's realizing, wow, that's a lot of wasted energy. Why would I continue to bypass 100 gallons a minute? So we get rid of those three-way valves, and we start replacing them with two-way valves. Now, as those modulate, we can do something with our pump. We can slow it down, all right? Now, now let's assume all valves are open right now, okay? And it's getting warm outside. The sun's shining in Portland anyway, and as our office heats up, we can start to throttle how much hot water we send to our zone or our VAV box. Okay, as we start to throttle that valve down or we close it, what happens to the pressure in our system? Now, I don't have a poll for you on this one, but I'll just tell you the pressure goes up. And the pressure goes up because a couple things happen. Water takes the path of least resistance, and pumps are stupid. They'll pump as much water as they can through the system. All right. So if we break this down into a pump curve, let's say we're chugging along, our pump's chugging along at 300 gallons a minute, okay, with all valves open. And we're putting out about 40 feet ahead, and we close one of those two-way valves. Well, now our pump says, well, wait a minute, I can't get 300 through the system. I can only get 200 through the system. And when you do that, you back up on the pump curve, and as a result, you see an increase in pressure. Okay, in this case, we've increased pressure by about 6.5 pounds of pressure. Now we can pick up that increase in pressure and slow our pump down. There's energy savings there. We close another two-way valve, and guess what? Our pressure continues to climb. And same thing, we slow our pump down accordingly. All right, so that's the importance these days. We've got two-way valves out in the system. We've got typically controlling on pressure or differential pressure. And we've got a drive that's picking up the change in pressures as our two-way valves modulate, and we change or fluctuate our pump speed accordingly, okay? And as we're doing that, we're also changing flow rates. Now, one might ask, if two-way valves are great, why don't we go to all two-way valves? And some engineers do, but we always need some type of flow to come back to satisfy not only minimum flow for the boiler, but also minimum flow for the pump and the system. So typically you've got some type of bypass built into your system so we don't deadhead the pump or go to a no flow condition. All right, so just kind of a quick history on where we were and where we are today. Let's talk about some different ways to approach various systems. One that's been out for a long time is called primary secondary. And to us, it doesn't matter which one you call primary and which one you call secondary. As long as you clarify it early, we can bounce on either description, all right? When you think about primary secondary, it should be really, the beautiful thing about it is we've got two independent zones. We've got a system out here, system pumps that are sending hot water out to various buildings, classrooms, offices. Any place we need hot water in this case. Typically controlled with two-way valves. We probably have a bypass so we can continue to flow back and circulate our building, okay? Now for us, most guys at CHC are going to call this the secondary. But if you prefer to call it primary, that's okay too, all right? Now, in addition to what we call the system or the secondary, we also have a set of closely spaced T's. And these T's allow us to come off of that system with some full line size and dedicated pumps for our heating equipment. Now this could be a boiler, this could be a chiller, this could be multiple boilers, multiple chillers, we don't care. The advantage of primary secondary is when we turn this pump on for the boiler, we circulate through the boiler, we come back, and now we can either go out to the system or return right back here through this piece of pipe we call a common. Okay? So the beautiful thing about primary secondary, you've got two two independent loops. You've got a system loop that's doing its thing, and you also have a boiler loop that can do its own thing, okay? It's beautiful for a retrofit. If this system worked before you got there, it's going to work after you leave, because all you've done is add some closely spaced T's, no additional resistance to our system pumps. That's pretty important, all right? This pump for the boiler in this case is simply sized for the piping between this T through the boiler, any pressure drop through the boiler, and back to this T. So this tends to be a fairly small pump. Very easy to troubleshoot, okay? That's a standard primary secondary system. Remember, closely spaced T's, dedicated pump. That's your indicator. Before I leave this slide, a lot of guys ask, so what's considered closely spaced on our T's? How close do we want to get them? Well, 3 to 10 pipe diameters is a good rule of thumb. So it really depends on your line size, but then 3 to 10 is a good rule. If you get them too far apart, spaced a long distance apart, you're going to get some friction loss in here, and you may get some ghost flow that occurs in your boiler circuit when you don't want it. So having them closely spaced eliminates that potential. And whatever you do, don't put a check valve in there or a balance valve. Okay, this piece of pipe is kind of sacred. Don't mess with it. Oh, begin pull number 1. So hang on, let me pop that one up for you. Let's launch a poll. Okay, now this poll is specific to the next slide, so bear with me. Let's get over to the next slide, and then we'll share results. Here's another example of primary secondary with multiple boilers in this case. And again, these could be boilers or chillers, but for this talk this afternoon, I'm just sticking with boilers. Now you'll notice, again, we kind of have some not so closely spaced T's, but that's all relevant based on scale and line size. You'll notice that each boiler in this case clearly has its own dedicated pump, and each pump is going to be sized for the amount of piping from the system back to the system. What's also not shown here, typically leaving each boiler, you might have a balance valve. So you're going to balance the flow from each one of these pumps so that each boiler has same flow rate, same delta T at high fire. Obviously, piping lengths could vary, but we're going to balance that in with some type of balance valve in the field. Now let's go over and look at polls. I see we're kind of split, which is fine. Listen, it's Thursday afternoon. The give a crap's kind of low. Let's share results. Let me drag that over. Is reverse return piping required and or critical for the boilers in a primary secondary system, just like we have shown? We've got yes, we've got no, and sorry, no idea. Listen, we're about a third all the way across the board here, so don't feel bad if you're in any one of these categories. We appreciate you taking the time to do a poll. So let me drive this home. If we're primary secondary, we don't require reverse return. Okay? You'll notice, and a good explanation of reverse return. This might not be the best slide, but we'll go with it. The first boiler getting served with system water, or cold water in this case, is going to be this bottom boiler. The last one returned is also this bottom boiler. So you'll notice that this piece of pipe comes over, up, and then makes a weird U and comes back. Technically, you don't need that extra piece of pipe. You could take the discharge of this boiler and tee it right back into the system. Because remember, we typically have balance valves on each one of these boilers, and that allows us to dial in our flow rate based on piping length. So in general, you do not need reverse return with primary secondary. Now, we'll get to another scenario where reverse return is critical. Okay, but to me, it's not critical on primary secondary. It's a good practice, but I don't think it's required. Now, let me continue on or power on. Now, let's talk about where reverse return is very important. And that's if we change it up a little bit and we go primary only. Or a lot of guys will call this very prime. all this means is that those system pumps that are handling flow out through our system, and all those zones are controlled with two-way valves and some type of bypass. Those pumps are not only handling the flow through our system, but also through our boilers in this case. Okay, so you'll notice that hey, these system pumps are handling flow out here, but they're also getting directed through our boilers. So here's our cold water supply to each boiler, leaves warm and heads back out to the system. Now, a couple things that are very important with this. These little green valves shown, forgive the schematic, but these aren't pumps. These are motorized isolation valves. Very important, because we don't want flow going through a boiler that's not firing. Okay, so these really direct water flow as we need more or less heat out here in our system. Pretty straightforward. Okay. The other thing that's very important about these, you can't close them all. Even if the boiler's not firing, you have to leave at least one of these valves open so that we have flow that comes back from the system and can continue out here through our system pumps. Okay, all that's controlled through the boiler control panel. It knows to leave at least one valve open so we don't run into some problems. Now, the last thing that's really important is your system pumps are being controlled by VFD drives, right? And they're responding to system pressures as your two-way valves are opening and closing. So flow rates and pressures tend to fluctuate. How do you maintain balanced flow through multiple boilers when they're piped primary only? The only way to do it, the only easy way to do it is what we call reverse return, okay? This is where it's very critical. So reverse return, this might be a better explanation. The first boiler served with cold system water, which I'm going to call this one right here is boiler 3, is the last one returned to the system pumps, okay, or the last one returned to the system. So one way to look at it, you got equal piping lengths on the return as well as the supply. But to me, it's easier just to follow a flow schematic and say, all right, this is the first one served with cold water. Is it the first one returned to the system pumps or the last one? In this case, it's the last one. So that's reverse return piping. Okay, we'll drive that home in just a minute here. So these motorized isolation valves, those are also very important. Now, we have a lot of engineers that say this is the cheapest way to do it because these are going to cost less than a dedicated boiler pump. Not really. These valves are about the same cost as a boiler pump, so it's kind of a wash. Your other challenge here is if you're in a retrofit, this can create some challenges because we have added some pressure drop to our system pumps. So you have to be careful with how you apply this. New construction, no problem. Okay, but existing, be careful. Now let's look at a typical mechanical room. We've got 5 boilers installed. Bear with me a second. And let's take a look at those motorized isolation valves. Now when you first start looking at the piping behind the boiler, nothing might jump out at you. So I put a circle around it. And if we zoom in, notice it kind of looks like a valve with a bulb on it. And if we zoom back out, you'll notice there's quite a few of these. Okay. In this case, we're showing 4. There's a 5th one that's out of view. But if we zoom in on this, or go to a cut sheet, I should say, you'll notice that this is simply a two-way motorized valve that's been insulated. And all it is a butterfly valve that is controlling flow to a boiler or not, as a boiler requires heat or not. Okay, so hopefully that makes sense. If you're going primary only, reverse return, and motorized isolation valves for more than one appliance. Primary, secondary, closely spaced T's, and dedicated boiler pumps. Okay. Another good example of reverse return. First boiler served with cold water is the one on the left. Here's a motorized valve. Okay, and it's the last one returned prior to our system pumps. So good indication of reverse return piping. Now that's going to be important in water heaters too, right? But also with boilers set up for primary only. Now, just to throw a wrench in the works, let's say we forget all this. We get all excited. We sell some high efficient condensing boilers, and you forget this little talk. And we pipe them direct return, or the contractor does, or us as the rep forgets to catch that little tick mark when we do a job walk. Let's just run through a scenario of direct return piping, okay, and the effects it has on our equipment. Now, each one of these boilers has a motorized valve on it. In this case, the lead boiler is over here. It's boiler number 1. And then you've got some standby boilers, in this case, boiler 2 and 3. So this one's 1 million BTUs. It's the baby of the group. And then you've got some larger guys as standby, each one of these at 2 million BTUs. The job in question is a pool application. So every morning they have to flush out the pool environment, get rid of chlorinated air that's been collecting all night, bring in fresh air. So there's quite a load in the morning. And then after that, you're maintaining the space, okay? So bear with me as I talk this through. Let's say it's, let me launch my next poll for you, and then we'll get to the scenario here. So this poll is specific to our little application here, okay? And then we'll share results as we go. All right, it's morning, it's time for heat. Okay, boiler 1 is charging away. We open up its motorized isolation valve. We get system flow that comes back. Okay, cold water, we heat it up and we send it out to the space. Everything is going great. No problems here. Until boiler 1 can't maintain set point out in the system. There's too much load for it to keep up. It's charging away, but it says, hey, I need some help. So what do? If we can't maintain set point, guess what? We bring on another boiler. So let's engage boiler number 2. What happens when we start boiler number 2? We open up its motorized isolation valve. And remember, water's stupid. It takes the path of least resistance. So water's coming back from the system going, hey, why do I need to go down here to boiler 1? I'm just going to roll through boiler number 2. Boiler 1 says, I was getting some flow, but now I have no flow. And guess what? When you have no flow through a boiler, it starts to steam or get excessively warm. As a result, boiler 1's off on its own high limit. Boiler 2's over here charging away going, hey, what happened to my buddy? He was helping me add heat. Now I'm on my own. So it's charging away. It's carrying the load. And guess what? If it can't keep up, you open boiler number 3. Okay, path of least resistance, all system water goes through boiler 3, heads out to the system. Boiler 2 is now off on a high limit. So you've got an owner with 3 boilers in his mechanical room, and unfortunately you can only fire 1 boiler at a time in this scenario. That's the problem with reverse return. If you had this as direct return. If you had this as reverse return, we would be flowing in from the left to right, and we would have balanced flow across all 3 boilers. So when we open one of their valves, they would all be getting the same water flow. Okay, that's important in order to keep our boilers online. Now let me end this poll real quick, and we'll just look at results. How would you propose correcting? Oh, yeah, maybe I should share results. Sorry. How would you propose correcting this boiler layout? Please select all that would be of interest. Make boiler 3 the lead boiler. That is an option, agreed, but every time boiler 1 or 2 was calling for water, there's nothing to force water down here. So that would still be problematic. Add automatic flow limiters to each boiler. Now, I agree, of all the choices, this might be one of the best ones that's, how do I say it, not so invasive. So you could add a flow control to each one of these guys to basically create some resistance and help force water to downstream here, okay? The trick is you've got system pumps on drives, and what do you set your auto flows to as far as flow rates go? You'd have to look at that very closely. Decouple the boiler system and replace motorized valves with pumps, basically turning it into primary secondary. So decoupling would simply mean we'd add some closely spaced T's here and a common pipe and replace these motorized valves with dedicated pumps. That way, every time the boiler was to fire, we would get dedicated flow through it because we have a pump that would kick on. Now, to me, that's the best solution, but all these are problematic after the fact. Add manual balance valves to each boiler. Now, I'm with you on manual balance valves, kind of like auto flows. The challenge with the manual balance valve, if I put it on the discharge of each boiler, system pumps are on drives. Manual balance valves work really good for constant speed, but as soon as a pump changes its pressure, like it would on a drive, you change the flow rate across the manual valve. So that can create a problem. Auto flows would be a better choice than a manual valve. And again, I'm not picking on anybody, just running through the options here, right? Write up the project manager and prepare for the change order. Yeah, this could get costly as far as making some changes. And sorry, no idea. Listen, that's why we're here today, is to discuss some options. Unfortunately, all these are kind of band-aids to a job that was laid out as direct return, but nobody caught it until it was started up and commissioned. So yeah, they're all viable fixes. To me, the best approach would be to go primary, secondary with it, or to try to put some band-aids and put auto flows on these boilers, okay? But a good example of a trouble job and what not to do. Okay, hopefully that makes sense on the importance of reverse return. It gives you balanced flow versus direct return, which we just ran through. You don't want to see this scenario on your project. Okay, so reverse return piping. Sunday, do we have any questions at this point, or are we doing okay?
We are all good right now.
Awesome. Okay, so let me look at a couple of examples with you. We're doing good on time. Now listen, I'm going to show you. This is a really good example if you spend some time looking at it. But initially, you might hate me, going, "Oh, this thing's a mess." and I don't argue with you. Listen, it's Thursday at 2:30. Yeah, your eyes are probably crossing already. One of the things that has really helped me to be a good troubleshooter or figure out schematics is using a highlighter. So I can take the same schematic and highlight it for you, okay? Now, I can tell you personally, this is kind of therapeutic. This is like going back into grade school and getting out the crayons, and you're off and rolling. You can choose any color you want. That's the cool thing about a highlighter, but it makes drawings pop. And all of a sudden, you can kind of figure out what's happening. If you're into a trouble job, don't be afraid to get out a highlighter. Every time we have a trouble situation, the first thing I ask for is a flow schematic. Let's see what's happening. Put yourself in the pipe. Your cold water coming back from the system. Hot water return. Okay, that's cold water. And where are we flowing? Oh, look at that. We're going below grade. Okay, well, that's interesting. And then we flow in here through our first boiler, which we call boiler 4. But we're also manifolded into 3, 2, and boiler 1. Okay, if the boilers are firing, I always assume all boilers are firing. We leave the boiler warmer. In this case, I went orange, okay, warm water, and we flow this direction. We go through an air separator. We head to our pump suctions, our suction diffusers in this case. Our pumps are putting out higher pressure, so I just change colors to go pink, and we're sending warm water under higher pressure out to the system. Pretty easy when you look at it, but if I go back initially, you'll be like, oh, this sucks. This might look a little easier, okay? Feel free to change colors. My one comment on colors, if you choose a bright red, it's kind of like driving in traffic with your heat seaters on. You tend to get a little agitated. So I stay away from bright red. It's just an anger issue, but any other color tends to be okay. Let's just look at this schematic real quick. First thing I'm always asking myself, primary, secondary, or primary only. So what am I chasing? Do I have dedicated pumps for each boiler? Do I have closely spaced T's, or do I have reverse return and motorized isolation valves? So let's just focus on one boiler. We're returning cold. We flow in here through boiler number 4. And as I leave boiler 4, I'm kind of paying close attention. What do we have leaving boiler 4? Well, you'll notice there's a little valve in here, a butterfly valve with an M stamp next to it. Well, M would mean motorized. That's a good thing. Okay, there's my motorized valve. Now the next question is, do I have reverse return? Well, which boiler is getting hit with cold water first? Well, that's boiler number 4. Which one's the last one to be returned to my system pumps? This one is traveling way over here, and then boom, it hits my system pumps. So first one served with cold water is boiler 4, and it's the last one returned, okay? Really good indication of reverse return. If you studied this drawing more, you'd really appreciate the work an engineer put into this. He's got venting, he's got gas rigs, he's got vented gas rigs, he's got control schematics, he's got control points, he's got flow meters. There is all sorts of things on here. It is really a good drawing, but initially, yeah, it might be a little overwhelming. Again, power of a highlighter. Whether you print it out on a copier and physically use a highlighter, it's what I used to do, but that's hard to do these days. Adobe or Bluebeam work awesome for that. And by the way, if you hold the shift button down, it draws a straight line. It doesn't look like you've had too much coffee. Okay, let me pull up another poll for you. I think this is specific to the next slide. Bear with me a second. Okay, it is specific. So let's take a look at this layout. Now again, it's not highlighted, but my next slide will be. So you've got 2 boilers shown here. Let me just move to my next slide, forgive me. We've got cold system water that's coming in, and it's flowing in here through, I'm going to call this boiler 4. And we've got warm water that leaves and then heads over here to boiler 3. Okay, we heat it up and we continue it over into what we call our system pumps. Now, a few things should stand out to you on this one. We have primary, secondary, or primary only. Well, I'm looking for closely spaced T's. And look at that. I'm going to start with boiler 4. We do have closely spaced T's here. Well, if we have closely spaced T's, we also have dedicated boiler pumps. Yeah, we do, as a matter of fact. That's what CP4 and CP3 is, okay? Circ pump 3 and circ pump 4. So dedicated pumps for each boilers. So good indication of primary, secondary. Now let me end my poll here real quick. Everybody's pretty strong on this one. Let me share results and drag them over. So the question is, are these boilers piped in parallel or series? Unfortunately, these boilers are piped in series, and this isn't something you want to do, simply because the output of boiler number 4 has an influence on the input of boiler number 3. Now, we've seen 4 boilers in series. We've seen up to 6 boilers in series. And the problem is the boiler closest to the return has 1 million hours on it because it's trying to carry the load. The further you get, or the further down the line you get, those boilers typically have 1 or 2 hours on them, simply because they can't operate very long before they spike on their own high limit, because they're getting influenced by all the other boilers that are sending hot water its direction. Okay, so boilers in series. The only time you'd want to do this is if these are truly lead lag, meaning that only one boiler is going to fire at a time. Okay. To fix this, you would take cold system water, you'd bring it in here to CP4, but you'd also continue it over here into CP3. So this blue line would continue over. The hot line that leaves boiler 3 would simply tie over in here to boiler number 4. Okay. So in primary, secondary, you only want 1 set of closely spaced T's. In this case, you got 2. That's not great. But again, power of a highlighter. You guys are doing great. All right, let's move on, or keep moving, if you will. So let's look at this guy. Let me throw a highlighter on it just to make it easier on everybody. And I've got reminders, so I've got another poll to bring up for you. There we go. We're getting close to the end, so hang tough. Okay, so let's highlight this guy. We've got two boilers, boiler 1 and boiler 2. We've got 2 system pumps. So the question again is primary, secondary, or primary only. Cold return water comes back from the system, flows down in here, kind of goes through a weird little bullhead T, if you will, and then flows into boiler 1 and boiler 2. You'll notice that the engineers only labeled one of these, one of the boilers, not the other one. But we're looking for either dedicated pump or motorized valve. And you'll see, if I got this highlighted, that we have an electric actuator, okay? That's your motorized valve. And then hot water comes out, goes through our system pumps, and heads on out to the system. Now, is this truly reverse return? It doesn't look like it. It looks like boiler 1 is the first one served. It also looks like it's the first one returned. But am I going to pick up the phone on this? Probably not. This is probably just a schematic. It may not be accurate to the field, but it's something to note. The other thing that stands out on this drawing is we've got a weird bypass in the mechanical room. Now, this particular engineer doesn't, how do I say it? Doesn't design around 3-way valves in the system. Only wants 2 ways out in the system. So when they all go closed, there's a potential for no flow in the system. That's bad for the boilers, bad for the system pumps. So how do you resolve that? Well, one option is to put a bypass in the mechanical room, okay? So if flows become too low in the system, now you open up this bypass, you send some hot water from the mechanical room or leaving the pumps right back into the return of the boilers. That's an option. You have to write a very complicated sequence of events or sequence of ops to make that happen, but it's possible if you have a flow meter and you set your parameters correctly, okay? But again, by highlighting this drawing, a few things stand out, and as you start moving across, you're like, oh, wait a minute, what are we doing with this piece of pipe? Strikes up some conversation. My last one for you. This one's hot off the press. So I've got some internal banter going right now, or an internal test with CHC on this particular schematic. So if anybody from CHC is listening, I'm going to give it away right here, okay? But this is a good example of a 20-story high-rise apartment building. There's about 420 apartments in the building. 80 are currently being occupied. This is a water heater schematic, not a boiler. So we're dealing with water heaters and storage tanks. The issue is it's taking individuals 10 minutes to get hot water when they wake up in the morning, okay? That's a long wait for a shower. and people are getting a little upset with that, okay? So everybody's wondering what to do. So send me a flow schematic. Let's look at it. So what you've got here is the yellow line is cold water supply, okay? So cold water coming in, happens to be an 8-inch line, size for about 800 gallons a minute. It's a lot of flow, 420 apartments, okay? You've also got a red line that goes down. Remember, red could be dangerous, so don't look at that line too long or you're going to get really pissed on our class survey, okay? But this is just tempered water that's leaving our master mixing valve. We've got a storage tank over here, and that's keeping water about 140, and 140 is tied into the hot side of our tempering valve. On this other side, we've got water heaters, and I call each one of these 1,000,000 BTUs, but all they're doing is circling back and forth to this storage tank to keep it at 140 degrees. So the advantage of a highlighted drawing or flow schematic in this case, when somebody's using water, okay, it's an open system, which means we're flowing water through our city line. That city water can either get into the cold side of our tempering valve or master mixing valve, or it can continue over where it ties into our storage tank, picks up some hot water, and brings that hot water into the hot side of our tempering valve, okay? Hot and cold mix to give us tempered water to send down our riser so we don't burn anybody in the process, but there's hot water available. All that's great. Now, everybody in the apartment go to sleep, okay? It's 2 in the morning. Everybody's in fetal position, snoozing away. In that case, it's a closed loop system. There is no city water flowing because nobody's taking a shower or washing their hands or doing laundry. They're all sleeping. So this tempered water line that goes down through our riser starts to cool off, okay? It gives up some heat, losing it to insulation and ambient. So what do? We turn on a circ pump, and we circulate that line. So our recirc comes tight in here, picks up warm water from our storage tank, comes and serves the hot side of our tempering valve with the goal of sending tempered water down our riser to keep it warm, okay? And comes back cold. We pick up some heat, run it through our tempering valve, and down we go. Everything seems fine here until you realize, wait a minute, guys are waiting 10 minutes to get hot water in the morning. Maybe we're not keeping this tempered water line as warm as we should. What are we doing wrong? What's the fix? Okay, so this, if you know tempering valves, this should be really obvious. Our recirc pump is only tied into the hot water side of our tempering valve, right? It only gives us access to the orange side of the valve. We have no flow through this yellow line. So if this port is closed, we are basically deadheading our circ pump. And if we deadhead our circ pump, then this line really gives off temperature and cools down. Now, when somebody starts taking a shower, we start bleeding water off of this line. Meanwhile, cold water is coming in and giving us accurate flow across a master mixing valve so that we can temper it and send that warm water back down this line. That apparently takes 10 minutes. So the fix to this is to, how do I say it? Deal with the tie-in for our circ pump, correct it. So we always want our recirc to tie into our cold water line so that it can either pick up heat from our storage tank or a water heater or continue on as cold water and serve either port of our tempering valve, okay, with the goal of giving us flow out here to our system so that this valve can modulate to maintain tempered water. Now, another good example, or maybe a better detail, if you will, sidearm water heaters serving the storage tank. This is how we'd like to see it. And then our cold water and our recirc tied together so that they can either go through the storage tank and pick up warm water to the hot side of our tempering valve, or come up here through to the cold water port where we can mix and maintain tempered water out to our system. So if I go back, you'll notice that they didn't do that. There's no way for this recirc to flow back here and hit the cold water side of our tempering valve because there's a check right there. Okay? They can either take this check and move it back here further by this isolation valve, or they can take our recirc and tie it in right here near the isolation valve so that water can either flow through the cold side of our tempering or come back here to the storage tank and pick up temperature. But power of a flow schematic, okay? They wanted to do a lot of other things in the building. As soon as I got to this little area, I'm like, oh, we got all sorts of red flags here, okay? Power of a highlighter. Okay, how are we doing? We're sitting at 2:45. I hope that helped everybody. If there's any questions, it's a good time. If not, we'll wish you a good afternoon.
Looks like we have a couple, Paul.
Okay, yeah, please.
Would you suggest a tankless water heater in series?
In series. I have to think about that. So we do sell tankless water heaters, but they still need to get piped reverse return And I would tell you that they're in parallel. So no, each heater should have its own source of cold water. So no, typically we don't go in series. I think that can be dangerous as far as how you're going to try to control your water temperature leaving them. It depends on the manufacturer. I can tell you the line that we represent, we wouldn't recommend that. We would still do them in parallel like we do for most primary, secondary applications, or primary only, right? Yeah, good question.
Okay, and one more question. How often is imbalance of flow really a problem in systems? Pressure drop changes with the square of flow, and if equipment is closely placed, 2 or 3 boilers on a skid, then the piping pressure drop difference should be minimal between them with a full-size header. It seems to me that flow imbalance would be minimal in this case. I can definitely see more of it with equipment which is spaced farther apart.
Yes, and I don't disagree. If I go back to, it's a really valid point. If I go back to maybe this schematic where we might not be looking at equal pipe lengths. We might have a little bit more flow going through boiler 1 than we do boiler 2. Is that really a problem? I don't know. We won't know until we do a startup, run through commissioning. So to your point, if you've got boilers closely spaced on a skid in a mechanical room, and you're off by a foot or two, is that the end of the world? I'm going to tell you no. I'm with you on your point. Your delta T might be a little bit different between boiler 1 and boiler 2, but is it enough to cause a major problem? No, I don't. I agree with you. My answer is no. But you have to be careful. So if your drawing's not to scale, people can space those out and get themselves into trouble, right? If your piping gets too long. But yeah, it's a valid point. To me, it's always good practice to go reverse return. Sometimes you don't have the room for it, so you take your chances. But if your equipment's close together, I'm going to agree with you that it's not the end of the world. But in general, yeah, if you go direct return, you may run yourself into some trouble, depending on the size of the equipment and the pipe size. The example that I showed earlier on direct return, this guy right here, there was not a lot of flow in the system, which was another downside. The engineer laid this out based on a 70-degree delta T in the system, so there wasn't a lot of flow to deal with to start with. I think overall it was 40 to 45 gallons a minute for 5 million BTUs. So yeah, flow is really lazy. So as soon as you open up one of these motorized valves, it just wants to go there. It'd be way different if we had 300 to 400 gallons a minute rolling through a system. Okay, you could certainly, this boiler would create some resistance by itself and force it down here. But yeah, all depends on the system. Really valid point, good question. I hope I've answered that as best I can.
All right.
Thank you for your comment.
Any other questions? Okay. With lead lag boilers, is there a need for a primary secondary system if the second boiler is in use 10% of the time?
Hang on, I need to look at that question. Sunday, I'm sorry, can you restate that? Can you restate that for me? That might be the better way to do this.
With lead lag boilers, is there a need for a primary secondary system if the second boiler is in use 10% of the time?
With the lead lag boilers, and I don't know if we're talking series or parallel.
Bridget, is it series or parallel?
Yeah, forgive me, I'm just trying to better understand the question.
Yeah. Let's see. See if I can.
Bridget, it might be one we want to take offline and try to address better for you.
I can allow her to.
Yeah, that's fine.
Bridget, if you unmute yourself, you can talk. Oh, parallel, she said.
So parallel. Okay.
Okay. Hi, this is Bridget.
Yep.
So I have it's actually a chiller system, and the um, the chillers are redundant almost,
Yep.
but 10% of the time the load gets high enough where a second chiller might be used in the system. And so currently we just have a primary loop, but I'm wondering if a secondary loop would be necessary for this through the chillers or even cooling towers that I have. So it's
Well,
cool
so
water.
yeah, if you've got a flow schematic, that would help us. Most chillers are still gonna use motorized valves. Do you know how they're being isolated at this point, or are you
They
free
do have
flowing through both
motorized
of them?
valves,
Okay.
and in the past when I had a series of chillers that would come on together, I used primary, secondary, but in this case we were hoping that the chiller one chiller would be enough for the load and they would just you know, have a
Okay.
redundant
I think I
chiller.
Yeah. So is your problem when you open up a second motorized valve that it's too much flow for the system and your system pumps can't keep up at that point?
Well, we're in the design phase still, but
Oh,
yeah, I
okay.
just want to give them the best design.
Well, yeah. Okay, well, let me address this on the boiler side, which might help you on the chiller side. One advantage to primary only, like we're showing here, is the fact that all boilers are getting the coldest water returned from the system. If you're a boiler manufacturer and you're chasing efficiency, efficiency is always based on cold return temperatures, right? So we've always got the coldest water available to each boiler. So that's a big advantage of primary only, at least on a boiler plant. On a chiller plant, I think you've got to be, the only caution would be if you open up both valves, are you going to get too much flow through the system, or do you have to oversize your system pumps? And the other thing to think about, you're also going to split that flow by half for each chiller. So one condition you might need to look at is what's the minimum flow for each chiller? And do you account for that out here with a three-way, or do you go primary, secondary, and just put dedicated pumps on there? You certainly have an option. One option to do if you're going primary, secondary is to put variable speed pumps on each one of those boilers or chillers. So we're showing this as maybe a constant speed. More commonly, though, we're going variable speed. So you can adjust the speed of each pump to maintain a constant delta T across the boiler, or in your case, a chiller. So that's if you break it out as primary, secondary. So Bridget, forgive me, I'm not sure I'm answering your question directly, but there's a number of variables to look at or consider when you're in design. Okay, that might be one. If it's going to affect your system greatly, then either put a dedicated pump on here that might be constant speed, or feel free to make it variable speed. A lot of times boilers will have an output signal as they modulate their burner to control I don't want to say it, it's an output signal to control a pump. The chiller is probably going to have the same setup. So you could control this pump speed to basically maintain a constant delta T as your chiller ramps up or down in production. And meanwhile, you're still doing what you need to out here in the system. I'm not sure I've answered your question. Happy to take it offline if you want to send an email or schematic, maybe some conditions. Happy to help. But yeah, really good question. Okay. Sunday, any other concerns we need to worry about?
Talking to me?
Yeah, I think so.
Our question board is clear now.
Okay.
Bridget, our email addresses are on the slide that Paul is showing right now. So, you know, like Paul said, if you need further assistance, you have more questions, you want to walk it through, you know, and by we, I mean Paul, is more than happy to help you go through this. Any other questions before we end class? I think we're good. All right, everyone.
Thanks, everybody.
Thank you so much. I appreciate your time.